Today's presenter is Ted Sullivan, Senior Solutions Consultant at Lucidworks. Thank you for joining us today, Ted.
Hi folks. Thanks, Aaliyah. Like some of my colleagues, I've been building search apps for a while now, and one of my main lessons learned, and others too, is that every search application is the same, but everyone is different too. But there are some common themes that tend to recur. So in this talk, I'd like to focus on some things I've learned about what we call semantic search, which in my view is all search applications that involve any text or words. Now the simpler part of the title refers to some tricks I've learned recently that make the search engine appear to better understand what we mean rather than just what we type into the search box. And I'm particularly happy to be working with Apache Lucene Solr these days, arguably the best search engine out there, in my opinion at least, and it's certainly the most popular if you just consider the number of installs. Although I've also worked with many of what I now call the vendor engines or vengeance in the past. Currently my company Lucidworks has created an admin, security, content, and query processing layers for Solr that we call Fusion. Pardon the brief infomercial here, but Fusion is, in my opinion, one of the most exciting platforms that I've seen in my career. I'll talk a little bit more about it at the end of the talk. Mostly, though, I want to talk about language and how we use it in search and how we can make our search applications understand it a little better, which can make a big difference in usability, as we'll see. So search is both a technology and a linguistic or language problem. So what do I mean by this? Basically, that as engineers and system designers, we need to get our heads around both the technological and the linguistic aspects of the problem, and to do that through multiple languages. Now these are both difficult and important problems. We're getting pretty good at the technological ones, and certainly a lot of brilliant work has gone into the design of search engines, especially Lucene Solr. A lot of that work being done at Lucidworks, I'm proud to say. But the main language problem centers around the fact that we, as users, that is, speak a different language than the search engine does, and I don't mean English versus French or Chinese. What I mean is that we tend to describe what we want to find using words and expect the search application to react as we would do if we were talking to another person, for example. This means that the search application should understand what we mean, not just match on what words or terms we use to describe what we want to find. Getting this right, though, is the secret sauce, in my opinion, of this business. The language issues are, of course, pervasive in search, but they're not as easily tackled as engineering solutions that we use for scalability, performance, and fault tolerance, for example. The language concerns have to do with the quality of the results that we produce and how well they match the user's intent. That is, show me what I want to see. So in this talk, I want to discuss a few interesting techniques that I've discovered that may help. It involves getting the search app at least to appear to be operating at the same level that we do, the semantic level. Some of this involves some heavy lifting software, but there are also a few tricks that we can use to perform this magic on a lighter footprint. And this is particularly important at query time, where we don't have a lot of time for heavy CPU, for example. Well, as an experience to explain what I mean, I was building a demonstration ontology about music and another one about software technology, and I'll talk about ontologies later, using Stanford's Protege software. I was also using Google, which also came out of Stanford, and Wikipedia, sort of online sanity checkers. So I'd be searching for the same type of thing to add to my ontology, like singers, guitarists, classical music composers, or on a software technology one, NoSQL databases, and so on. And I'd be searching for the same thing repeatedly on Google. And after a while, the type ahead became a bit spooky. It would start to suggest names with just 2 or 3 letters entered, almost like it was reading my mind. I was kind of getting freaked out until I realized that it's as if the session state knew what type of thing that I was searching for. And Amazon seems to also do a good job of this because you buy different types of things on Amazon. So in any session, you might be searching for one thing or another thing. In my case, technology books or jazz records. So there must be some metadata that comes back with the suggestions that is used to boost what I'm interested in based on the type or category of the thing that I'm looking for at the time I'm doing the search. Because in a few minutes, I might be doing a series of searches for some other thing, and that then the type of. So one of the takeaways is that if we know what the user is looking for, and I'll go into that in more depth later, we can do a lot of cool things with that knowledge, even if we don't have the funding that Google and Amazon does. So that's one of the basic ideas. How can we do this on a simpler footprint, some simpler techniques, that is. And that's one of the basic problems I want to focus on. Because search engines, even Google, I'm pretty sure, although I don't know, initially work at the level of syntax or token streams, creating what we call an inverted index or a bag of words, as I call it, sort of less reverently. But building the next layer of language, that is meaning or semantics, is something that smart search applications like Google and Amazon do, and not so smart ones don't do. And these are the sort of techniques that I want to focus here on, how we can make our own search applications smarter. So a lot has been said about technology issues involved in search, as this slideshow talks about, many of which search shares with other information retrieval systems like databases, either NoSQL or the traditional RDBMS systems, and content management systems. And many of these problems, or technological problems, boil down to getting things done in what I call HTT, or human tolerable time. People have short attention spans, that is. So these are horizontal because they are not unique to search applications. And one of the overriding concerns in any application, whether search or not, is being user-friendly, whatever that means. Take them out for a beer once in a while or send them Christmas cards, I don't know. Anyway, but that said, the UI experience, or UX as the wonks call it, is critical, as is time to value. Getting good answers back before the user gives up and clicks off your website and goes to buy it somewhere else, for example. Another imperative that we're seeing and across all types of systems is to be constantly available and to service many simultaneous users. You know, think Black Friday here. This also affects getting back answers quickly, and to do so with incredibly large data sets. So we also have to rein in complexity, because all of these things affect complexity where we can. And that problem is, or should be, limited by Einstein's dictum that things should be as simple as they can be, but not simpler than that. And another example is maintenance costs, especially with complexity gets out of control, will dominate, especially if your application is successful. So dealing with high query volumes is, of course, a problem that we all want to have. So I want to show you a few things that could be considered simpler, that is, hopefully don't add to this CPU burden that we already have, but hopefully not simple-minded to get at the language issue. So let's look at some search issues, first from an analytical perspective and then from a more linguistic one. From the analytical side, we have some well-trod measures of search goodness, that is precision, recall, and relevance. Precision means getting all the right answers, or a few wrong ones. Recall means getting all the answers. Sorry, precision means getting just the right answers, and recall means getting all of the ones that could possibly be right. Whereas relevance puts a focus on what we mean by right and wrong. Maybe some answers are righter than others. But who's judging this? That is to say, relevance is contextual, as my Google ontology hunt shows. So we try to bring back as many answers as make sense to the user with as few clunkers as possible, and then we order them according to some criterion that we call relevance. Now, this is not a trivial problem to solve, as are the horizontal problems, and none of these are trivial. And my colleagues Doug Turnbull and John Berryman, it turns out, are writing a whole book on this topic. I think they're calling it Taming Search. That should be published in the near future by Manning Press. Hopefully it'll come out and you'll be able to see what Doug and John are talking about, which is all about relevance and how to boost it. And I'll say a few things at this point in this talk, but I'm not going to say a whole lot about relevance, more about precision. And these are slightly different things. Precision is a yes-no. Is this document about that topic or isn't it? Relevance is fuzzier and more subjective, and as we see, more contextual or dynamic. is this document more about this topic than it is about that one? Now, for some data sets, e-commerce being a classic example, precision is more important. For others, like bibliographic data sets, relevance clearly is the more important factor. So now let's look at this from a language perspective, more linguistic point of view. And this is one of my favorite examples. It's like the linguistic equivalent of those pictures that psychologists studying visual perception use, that is it the young woman or the old lady, and it kind of flips back and forth depending on how you look at the picture. The first sentence is pretty straightforward, even though it's a metaphor, but having your head around the first one makes the second one a flipper. That is, either you think of flying bananas or the little critters that love to feast on them. And it turns out I did genetic research in college on fruit flies and did crosses and counted thousands of little things. And I used to have dreams about them, but I don't remember any flying banana dreams. But as the slide says, depending on what word or phrase that we use to decide what the subject noun is, the verb changes to either flies or like, which is either a preposition equivalent to as or a verb, depending on the choice of noun. The object in this case is always banana. The language is full of stuff like this, and understanding what is being talked about is all about the context, in this case the lexical context of the sentence, but as we see, the second sentence can be parsed in different ways to get different meaning. So how do we handle all this kind of thing with search software? Well, again, there are these heavy lifting approaches that we call natural language processing that are out there, and some simpler tricks that we can pull to sort of simulate this semantic awareness that I'll talk about. Now, this is not to say that we shouldn't use NLP. It just is CPU intensive. It takes a lot of processing. So we tend to put that stuff at index time so we can then do the cool things, the little magic tricks that I'll talk about when the query comes in. So short of reverse engineering Star Trek's Mr. Data to figure out, true artificial intelligence approaches, but as an aside, one of the favorite Hollywood joke sources is this kind of thing in TV and movies, that is like having a talking computer attempt to figure out what a human is saying. One of my favorite examples of this is Jaime the Chaos Robot in Get Smart. I guess I'm dating myself here, but after all, my title is Senior Solutions Consultant, emphasis on the senior. So here are a few tricks that we do now using the algorithms that we already have. We know that certain fields like the title are more relevant than others because they already attempt to summarize the content. So we boost hits in the title field over other fields which have a lot of stuff in them where the concepts can get lost in the noise, both in terms of concept and in terms of just the number of terms, or numerically speaking, that is the TF-IDF. We also favor documents that contain all of the words that we enter in a search box over documents that just contain some of the words, even if they have more instances of the query terms. That is, we look for queries that favor queries that go broadly instead of in depth. And we do this with a simple trick in Lucene, which is to add or Solr, which is to add a coordination factor to emphasize documents that have more terms in them, rather than those that go deep in only one term. It's not perfect, but it covers a lot of ground with a simple bit of math, which is the kind of thing we're looking to do. We also prefer documents where the terms in the query are close together, preferably in the same order that we put them in. This is called proximity, or what Lucene calls phrase swap, which is one of my favorite technical terms. And finally, number 4, we eschew the use of AND, which is a more precise operator than OR, but can lead to 0 results, especially if there are typos and we don't catch them with our fuzzy spell checkers and all that good stuff. And besides, we have facets also in our search applications usually, which can bring us back to the results we want back to the top, but the facets won't work if we don't give them lots of possibilities to facet on. So we opt for good recall over good precision typically because we have facet search to back us up. And one other thing to say is that in the old days, we'd be happy if we could tune our relevance algorithms to bring back the top or the best answers on the first page of results. But a few things will trip us up at this point, faceting and now mobile search. In Solr, faceting occurs at query time. Facets are calculated, that is, on the fly after the doc IDs are collected by the initial pass. The faceting engine therefore sees all of the results, not just the top ranked ones. I actually found some interesting errors this way in search apps. And we want it this way because we want to give the users the ability to refine their query by drilling in using facets. As we'll talk about later, this paradigm is going to become less important with mobile search. But because facets look at the entire result set, the facets see everything, even the blemishes. So improvements in precision can mean a lot when we use faceting. We clearly want to eliminate the wrong answers, so we only have to sort by relevance on what's left. That also gives us performance gains because sorting and faceting are two of the most expensive computations that Solr has to do. And improvements in precision are very important for mobile, where we may only have a page of 1 or 2 records rather than 5 or 10 that we need to send back or risk losing the customer. So one of the takeaways that I want to emphasize in this presentation is that phrases are very important in language. We as humans know this, but to get at them in search technology, we need good ways to detect them in the text, in the query that is. So many of the ambiguities that we deal with simply go away when you consider noun phrases rather than tokens. Not all of them, of course. There are still ambiguities left after you do this, but this is not a one-trick solves all problems world. We can also deal with phrases on the fly, as the Solr Dismax parsers do when they deal with proximity or SLA. And dealing with phrases linguistically, as I said, is also possible using a set of technologies that we call NLP. And there are many good uses for this technology, but many of these processes are computationally intensive. Not that this precludes their use, of course, but it does affect where and when we can use them in order to pay this human tolerable time imperative. And I'll talk a little more about that later. So recognizing noun phrases is a very important part of a process that I call query introspection, where we're basically using, parsing the query not just for our own syntax, but also for the semantic context. And one way to do this is to have a knowledge base that knows already what the important phrases are for the knowledge domain that we're searching, the so-called key phrases. I'll go into later about how we might get such a knowledge base, but for now, assume that we have one, either for autophrasing or for autofiltering, which I'll talk about. But how we ever get to such a knowledge base is an important thing, of course. But the epiphany that I had a while back, courtesy of my colleague Eric Hatcher, is that many of us have already built one. We've already built a knowledge base that we can use for query introspection, but we call it our search index or our collection. That is, we already have it. And one of the tricks that I'll introduce is how to leverage this knowledge base, which is our search collection, to do query introspection. And this is a technique that I call query autofiltering. It's a bit incestuous. We use the search engine's own stored metadata to better search it. But that's okay. The collection is the best source of information about itself. And in many domains, we've already done a lot of work to make sure it has good metadata. Usually I mean e-commerce, where we have these string fields. And the string fields, as you'll see, contain these noun phrases that we're searching for. But first I'm going to talk about an older technique that I introduced called autophrasing that doesn't use the collection's own metadata. And some collections, like bibliographic ones, don't have much metadata anyway that's of use until we get some, and I'll talk about that later. So we need to give it one. We need to give it a set of data. So one of the ways to improve things is to explicitly, as I said, to explicitly tell the search engine what token patterns constitute important phrases. And autophrasing is a technique, and it gets its name because we inform the search engine about phrases, noun phrases that is, that represent single things or concepts. So autophrasing requires an additional knowledge source, which is this autophrases.txt, a flat list of phrases that should be treated as single entities. There's also a technical issue in Lucene Solr that autophrasing can help solve. how to deal with multi-term synonyms. Now here's an excerpt from a Solr JIRA ticket, 1622, that expresses the problem. Basically what happens is that when you tell Solr, Lucene, that two phrases are synonymous, you get cross hits on parts of the phrase that are unintentional. I'm a New Yorker by birth, so this example kind of resonated with me. Also, the term apple is used in this example, and it's also in a blog post that I published about this. And one time, Grant Ingersoll, our CTO, was doing a meetup, and he indexed our website and searched for Apple computer, just typed in Apple, and my blog post came up. One of the worst examples of a mishit. That's a wrong hit. My blog post has nothing to do with Apple computer or apples or any kind. It just uses the synonym Big Apple for New York City. So there's a technical explanation for the multi-term synonym problem that's known as Sausagization. And this is by that awesome force that is Mike McCandless. If you really want to learn Lucene, you should get Mike Aircatcher and Otis Gospodnetich's book, Lucene in Action, and also read Mike's blog posts. But the bottom line is the JIRA tickets involved in this are a little old by now, and meaning that they might not or may not get solved anytime soon. So when that happens, we look for a workaround. And there are a few Solr tickets right now that will hopefully solve the multi-term synonym problem, and I urge the committers to put one of these into release soon. But that said, there are some cool innovations in Solr 5 where you can just add custom jars to make it easier to deploy custom solutions. My own solution, for example, is on GitHub, so you can use it right now if you want. I know people out there actually are using it. Anyway, the autophrasing can solve the multi-term synonym problem by simply making it go away, by making phrases into single tokens. Then everything just works. So here's a demo that I published that shows how this is set up. On the left-hand side are a list of phrases that I want to be treated as single concepts. On the right is a synonyms file where I have related terms and phrases, where I've related these phrases. Now the underscore character on the right is basically used just to keep the character positions in sync, mostly for highlighting purposes. But as you see, I have a one-way synonym of New York, which can mean either the state or the city, and then the various phrases that mean New York State or New York City. And then the bottom two are bidirectional or two-way synonyms to map New York State phrases and New York City phrases respectively. And then indexed a bunch of data that was basically tried, yes, but I've actually used this autophrasing technique recently in a production application on Fusion, and it works with real data. It just removes the problem of phrase ambiguity for in certain situations. So this is basically comparing the out-of-the-box select handler on the left and the custom autophrase handler on the right, and you can find details on this on my blog posts or in the GitHub distribution. So the phrase New York is ambiguous. It can refer to either the city or to the state. And the autophrasing solution gets it right. It brings back every document, which is what it should, because they're all either about New York State or New York City. The same thing with the New York City and the New York State queries. In this case, the autophrasing handler gets it 100% correct. The New York City responses are only about New York City, and the New York State ones are only about New York State. Whereas without any help, the Lucene Solr search application using the select handler does a pretty poor job in terms of precision and recall. To be fair, though, I didn't show the relevance results here, where the select handler actually does a better job. So the New York City records would probably rank higher than the other ones, the mishits, the wrong answers in terms of relevance. But this is more about precision. The autophrase handler scores 100%, and the out-of-the-box select handler does not. Another example that I did is just searching for Empire State. It looks like they're both doing perfectly right. Only the results that come back are about New York State. However, there's a simple explanation for why the select handler is working, and it gets to how it actually does work. If you notice, all the documents that come back have either the token state or the token empire in them, So this is a bit of luck on that part of the select handler. It's not looking at phrases, it's looking at individual tokens. And there's also some bugs in Lucene, notably Lucene 2605, that make it difficult for Lucene Solr to handle phrase queries without messing up. And this is a bug that means that the select handler really can't see the phrase. Even if it adds synonyms, it wouldn't really be able to deal with it too well. Okay, so switching gears a bit, let me introduce this newer concept of query auto-filtering. And as I said, this idea was inspired by my friend Eric Hatcher, but it's similar to some of the things that I had done in the past, in which you use a knowledge source to help infer what the query is about. And this is a technique that I call inferential search. Basically, what this boils down to, in this case, is creating a fielded query in Solr terms, Solr Lucene terms, from a free text query by detecting the noun phrases in the query and then mapping them to search fields. The best example of this, of inferential search that I know of, is if you search Google for your city, wherever you live, then the words weather report, or your city, and then the word forecast, it just gives you the forecast, the weather forecast for your area, not the documents that have those particular terms in it, because Google has figured out that what you want is a weather report, not documents about weather report or your place of origin. So another example of that is if I tag documents that talk about Microsoft, and this is the tagging process that I'm showing on the slide here, the content tagging upper left, upper right, sorry. If I tag documents that talk about Microsoft, and that term is then used in the query, I can use the same metadata that I put into the search index to improve the query using this technique that I'll show you in a minute. Even if the document is about Microsoft, but that specific term was not used in the tagged documents. Rather, maybe the document talks about things like .NET or Windows 8 or C#, Xbox 360, SharePoint, Internet Explorer, etc. Microsoft has created a lot of products in its time, and there are a lot of noun phrases that are related to Microsoft. So the basic, and I'll talk a little bit more about how we use taxonomy ontology to do some of that stuff later, but the basic process is to tag documents at index time, either by some funky classification processes, NLP, machine learning, taxonomy, whatever, or manually using a bunch of subject matter experts. And then you index the data, or you can index the data from a database where that metadata is already created. That's the box, as I said, labeled content tagging. And what you get out of it is metadata, field value pairs in the search index to help describe what each thing is, what each row or document in Solr or Lucene terms, and what properties the documents have. So that's not a too uncommon thing, right? A lot of us have this metadata already in our indexes. Well, and we typically use this stuff right now to do faceting. That's what it's really good for. Well, query auto-filtering simply leverages the same information to do query introspection. And this shortens the loop. In other words, it cuts right to the chase. Rather than waiting for the user to enter a query, giving them back a bunch of results, and drilling in, we just skip the drill in part and we jump right to it. Google calls this I'm feeling lucky. But I hope you'll agree with me that it's not luck. Here's the secret sauce, Lucene-wise, the so-called FieldCache. Now, the public API for the FieldCache has undergone a name change in Solr 5. It's now called the uninverting index. What this translates to in human speak gets really to the heart of what search engines do and how they work, including Lucene. As I said earlier, all search engines first split up text or tokenize the text into these tokens and then create an inverted map of the token to the document set that contains the tokens, so that when you search on a token, the search engine will bring back a set of documents that contain this token or a synonym for it. And Lucene does this very rapidly using bit sets. Lucene also contains a forward index to remove the double negative here of uninverting, where you find all of the terms or doc values is another data structure that have been indexed in a particular field. And so the FieldCache, for example, is a very important data structure for faceting. And we can also use it for this auto-filtering trick. So here's the basic implementation or the magic trick behind auto-filtering. We use the FieldCache to build another backward map. In this case, we're mapping field values. It's a many-to-one map to field name. So we're mapping a value that's in the field that's been indexed in the term vectors to a field name. We also pile in the synonyms into this map and also do some stemming on it, because we're eventually going to settle on these Solr string fields, which are have exact match semantics. So we need to do something to make them a little more flexible. I also built in a rule into the query auto filter that the longest continuous phrase match wins, at least initially. There's some other stuff that happens in the logic. But this helps us disambiguate phrases like New York and New York City and New York State. If the phrase is New York City, the autofilter will glom onto that rather than the shorter phrase New York, for example, because it's more specific, it's more precise. And so it's a lot like the Autophrasing solution, but in this case, the autofilter doesn't rely on a separate file. It just uses the data that's already indexed into the Lucene index, courtesy of the FieldCache. So a little technical detail here. Here's how we configure Solr to use this auto-filtering component. Once you have the jar file, you build that. This is a snippet from the Solr config XML. And as you can see, if you can read these things, that the auto-filter is a search component, which means it's part of the query processing chain that we have built into Solr. And the query processing chain is responsible for taking the URL and turning it into an API call against Lucene. And we set up this auto-filtering component as a first component. That means that it sits at the top of the request handler chain, so that it sees the query before the query component, which is the standard query processing thing, which includes the query parsers. It sees it before the query component has a chance to see it. So the auto-filter can essentially rewrite the query if it detects noun phrases that it knows what to do with. So to show off what it can do, I created a small test collection using the concept of products that might be found in a fictional department store. A real-world example would be Target or Walmart. And obviously the real data sets are much larger, but they do typically contain metadata like this. Maybe not exactly like this, but it has this flavor. So I deliberately built in some ambiguities here. But in the real world, of course, there are many examples of this and have produced some interesting war stories in the e-commerce biz. Things like J. Crew, which is a manufacturer, and Crew Socks, Joe Boxer, which is another clothing brand I found in Kmart once, and boxer shorts, Old Navy, navy blue shirts, lots and lots and lots of examples like this. So this just shows the basic behavior of the query auto-filtering component. So for simple queries like red sock, the autofilter will detect that the token red is a value that it's seen in the color field, and that sock is a value of the product type field. So then you can either set it to do a filter query or an FQ in Solr terms, or a boost query or a BQ. Now the filter query will only bring back the records that have these field values exactly it will map to the exact value as you'll see in a moment, whereas the boost query will just help bring these things to the top. And boost queries, as I said, were probably more useful in bibliographic stuff, the Microsoft example being a good example of where you'd probably use a boost query rather than a filter query. Now the second example shows the longest contiguous phrase rule, as they call it, at work. Now red line is an actual brand of soccer socks. So the filter would first read the word red and say, okay, that's the color, I know that. But then when it matches on the longer phrase, red line, it will then reject the shorter phrase, red. So it will only come up with the FQ brand as red lion and product type socks. It even works fine if you search blue red line socks, for example, because then blue is a color, blue red is nothing, red line is a brand, socks is a product type, for example. But what if you search for purple socks and there are no purple socks in the database? What should it do? Well, the filter query will return 0 results, which is actually correct. We don't have any purple socks. And I think that this is actually kinder and more friendly than returning a whole bunch of purple things that aren't socks and a whole bunch of socks that aren't purple. And I wrote about this in my first blog post on query auto-filtering basically the argument is that we should try to speak truth when we can and not assume user error. But we often speak falsely because we don't really know what we're returning back. And when we do, when we actually know that there are no things that have been labeled purple, colored purple, and our socks that we sell, then we should just tell the customer that. Again, we can do this when we know what we're returning. The third example shows how synonyms work. And if you have a synonym for chaise lounge, is lounge chair, and we're dealing string fields, you need to translate the query to the exact value because string fields are typically not analyzed, as we say, although you can do that if you use the keyword tokenizer, but that's another topic entirely. Also, we use stemming in the autofilter so we can handle plural singular matches where we're dealing with exact fields in the back end, for example. So users will tend to put more information in the query and they expect to get more precise results. And without tricks like these, the search engine will just bring back more stuff, i.e., you give it a more precise query, it actually returns a less precise result set. So in one example of this data set, if I queried for men's white striped cotton short sleeve dress shirt, and when I ran this one through the app, the select handler brings back 131 out of 164. I said it's a small data set. The auto-filtering handler brings back just 1. So that's a very serious improvement in precision, and all it requires is that we know how to map these long queries into fielded queries, which the auto-filter does. And I should say that queries like that, men's white striped cotton short sleeve dress shirt, is probably not very common right now in Google, but these are going to become much more common since we can now talk to our cell phones or search apps, that is, courtesy of our phones. So we're going to see a lot more of these long, woolly queries as we go. So the query autofilter can be a useful tool for improving precision or relevance, given that we have structured or data or metadata. What about when we don't have that, when we have what we call unstructured data? Well, first of all, the word unstructured is a bit of a misnomer in my opinion. Text is not unstructured. It's just that its structure is based on linguistic rules that we understand, but making the computer understand them is a bit more difficult. Remember the slide with the flying bananas. So we have some classic techniques that we already know how to use to pull structure out of text. This slide also attempts to make the point that little words like the word if can matter a lot in terms of meaning. And the example here of the Rodgers and Hart song and the Disney movie really differ only by what we would normally call stop words, that is, words that we don't consider. And there's also a famous phrase that Shakespeare wrote, composed entirely of stop words, to be or not to be. So again, the phrase matters, even the little glue words that we use to build it, the prepositional words, for example. And as the slide said, little words like if can have important consequences. It's an important pivot word in our language, in other words. So we have a lot of techniques that we already know about for classification, broadly lumped here into machine learning, NLP, and taxonomy ontology. I'm not going to get into evangelism here. Like anything, each of these tools has its pros and cons, and has good uses. That is, using a hammer to drive with a screw can be a pretty painful experience and ultimately will not succeed. So NLP is a good way to parse written text into its component parts, and can be very useful in discerning structure within unstructured text. And again, I put that tongue-in-cheek because it's really not unstructured. It's just we have to figure out how to pull the structure out. Machine learning is a good way of using statistical analytics, kind of like a bag of words approach that the search engine uses, to find similarity or co-occurrence of terms in documents. And it's popular, I think, because there's a perceived low cost of entry, although this low cost can be deceiving when you get into these semi-automated approaches where you have to build a training set and you need to pick some documents and you tweak the training set and you have to crunch large amounts of text to get it so its performance approaches some threshold where people won't laugh too much when it returns results. Now, taxonomy ontology is perceived to be expensive, and they can be. However, you can use NLP and other approaches, as I'll talk about, to build ontologies For example, Thomson Reuters Open Calais is an example of this. They have a huge ontology, and it was largely built using classification rules and techniques that are not ML types of techniques mostly. And so, yeah, but another important difference between those is that the machine learning techniques can tell you that two terms are related or correlated, but they generally can't tell you how or why. So in my Microsoft example, it might tell me that Microsoft is related to .NET, but the ML wouldn't necessarily know that .NET is a platform that is used by Microsoft for most of their applications. So NLP and taxonomy, of course, can give you these relationships because they know what is related to what. And for query auto-filtering, these relationships, knowing what it is and what it's related to, is very important, and as I'm showing you, it can be used in a lot of cool ways. So here's an example of using ontologies to generate this structure. So if I have a taxonomy, I can have what I call evidence nodes on the right. These are usually leaf or instance nodes, like a Beatles song or a composer name, for example. And category nodes, that's parent nodes that contain some of these evidence nodes, like composer or song. So if I have a music ontology, in my music ontology, I have composers as a category, and examples or evidence nodes like Beethoven, Bach, Mozart, Duke Ellington, Ray Charles, Elton John, Sting, many others like Robert Johnson, for example. And I use these noun phrases as evidence nodes. So I have compositions as another type of node. These guys would have a lot of these compositions, and there'd be relationships between, who wrote what music, who covered what song, and so forth. It's too bad Beethoven wasn't alive now, because we probably have some pretty cool recordings from him if he was able to. So I can build a classifier from all of this stuff by letting the mentions that hit on an evidence node or as a vote that the document is about some category node. And the further away that the category node is from the evidence piece, the weaker the vote gets. And therefore, I can score documents according to the best categories. That is, the category nodes that collect the most votes from their evidence nodes. So in the next slide, I'm going to show you just a little walkthrough this, a thought walkthrough that is. Here we have a skeleton company ontology that has a few dimensions, like the vertical that they're in, the nationality, the size, whether it's a Fortune 100 company, for example. And these types of ontologies are out there in the marketplace. And Thomson's, for example, Thomson Reuters has a very comprehensive one. It's constantly updated, and you can actually use these. They're not cheap, though. But as I said, this talk is about simpler and not necessarily cheaper ways of dealing with semantics. So if I have a document that mentions Ford, GM, and Chrysler, I would prefer at that point that this document is about U.S. auto manufacturers. But if I also find Toyota and BMW mentioned, then we're still talking about auto manufacturing, but now it's a multinational scope. If I then add GE and Boeing, I'm still talking about manufacturing companies, but now not just of automobiles. And you can imagine that if I added banks and hotel chains to this list, and these are all contained in a single article, for example, it might be more accurate to say that this is about large companies and so on. So the terms that we use to classify that those are related to a concept, in this case auto manufacturers or manufacturers. We can then, once we tag documents with this concept, we can boost documents that have that concept in the query, even if the concept term itself, manufacturing, for example, is not prevalent in the document, but the evidence terms that are around it are related to it are. So, slide doesn't want to change here. Sorry about that, I jumped 2 slides. Apologies for the delay here. There you go. So here I want to introduce what I call a basic search use case in the remaining minutes, which basically involves formulating a query. The search application then brings back results, and then the user refines the query. And typically, this involves a cycle where either the results are satisfactory and everything is good, and the user clicks buy or something, or they get further queries. And the slide lists some of the traditional ways that we try to enhance this by shortening the loop, as I'll talk about, like snippeting, highlighting, faceting, and so on. I'd also like to stress at some point that many of these traditional mechanisms work much better on a PC with a 38-inch monitor than they do on a tablet or a smartphone. And the other thing is that we want to get the user the answer they're looking for as quickly as they can, whether they're on a PC or on a Droid. And in the bad old days, search without good precision often involved a lot of hyperlink clicking and then searching the search term again in the document once they brought it up to see why the document was returned in the first place. So people tend to form ambiguous queries in the first attempt, so getting too many results and having to manually inspect them is tedious. So we need ways to speed it up, to shorten the loop, in other words. And there are a lot of things that we do now, including the type ahead, the auto-suggest that I was talking about with Google, that provide shorter time to value. Recommendation is also another good one, boosting documents that have been found by previous users to be related to the query. Best bets is sort of a way of forcing the right answer, and this is usually judged by a subject matter expert. I call it punting because you're really just manually suggesting what should come back with the result. My favorite example of this is the holiday schedule. And this is a case where you know what the user wants in enterprise search. They want the holiday schedule. They don't want documents with the word holiday and or schedule. Solr calls this thing the query elevation component. That's a very useful component. Best bets is kind of a manual way of doing what I call query introspection. That is, you have a person looks at the query logs and decides what the user wants rather than a machine. And I've added query auto-filtering to this list because it's also a way to shorten the loop. Rather than having the user search and then drill in using facets, we just jump to the query that would have resulted from that. And I would submit that this is particularly useful for e-commerce data where we have high structure on mobile technology where there's not a lot of room for scrolling and faceting. You just basically want to bring results back because these other activities that the user used to have to do would be an experience killer on a mobile phone. So finally, in the last few minutes, I want to talk about what we call pipelines. That is, the query auto-filtering component is an example of a Solr search component, which is a part of the Solr search processing chain. And as you should be aware, if you work with search applications, there are two basic types of pipelines, one for indexing data in and another for querying. And I've been sort of talking about these already, but I wanted to go through some formal things. Now, designing a search system usually involves a coordinated design of these two pathways and basically should be considered from a user interface perspective first. That is, what information do I need to get into my search index via indexing pipelines that I can then leverage to build a user interface, maybe using query pipelines. So we traditionally do the first part using these so-called indexing pipelines, which I call good old ETL, or extraction, transform, load. And basically what happens here is that the pipeline processes the data and puts it into the index. So I want to actually focus on language here. So one of the really cool things that you can do with index time processing is that you can build these extractors that work on more than one level using an intermediate payload called annotation. And both Apache's Uema and the Lucidworks Fusion use this process. So what happens here is that we can use these pipelines to discover these so-called triples or subject, predicate, object fact relationships that we find in text. And the really cool thing here is that you can build these things out of piece parts. So entity extractors will identify the subject and object noun phrases, and then we use annotations to sort of mark the location of these entities in the document. And then once we have the entity extracted, we can then use patterns, as shown on the right, to basically join these entities into facts. And this is a simple example of a pattern so you can see how they work. Some of these packages have some very sophisticated languages, Smart Logic, OpenCalais, for example, where you can describe these linguistic patterns in very good detail. It's kind of like linguistic equivalent of regular expressions, if you will. So in this case, we have a bunch of patterns, and then we can detect facts. And it may not be well known that IBM's Watson basically used this technique to crunch huge amounts of text to build a very large ontology of these subject triples using UEMA. And basically what happened is they were able then to use these triples to win Jeopardy, as we all know, because that's basically, as the slide says, a guess the subject given the object and the verb, but you have to pose your answer as a question. That's the easy part. And Watson had like a ton of PCs in the background to make this so it could do it in not just human tolerable time, but human whooping time, if you will, which is, I felt, a little bit unfair. But what about query pipelines? I'm running a little late, so I'll just do this as quickly as I can. We can do a lot of things with query pipelines. This basically gets to the question of who is searching, what are they searching for, where are they when they're searching, and when are they, what of interest in the timing of the information. So for security filtering, we have the who are you, what can you see. We also can do dynamic boost blocking based on preferences and search history. That depends on who you are. For where, we can use geofiltering to get answers to questions that rely on location, like where's the nearest Mexican restaurant for me. And we can do that either from the IP from your PC or even the GPS coordinates that's sent by your cell phone. Another interesting one is content spotlighting, and you can basically write a rule that says for something like show this product 3 months before Christmas to consumers from the Midwest that have a store credit card if they search for X, Y, or Z. And all these may involve things like looking up in NoSQL stores and such before you build these filter queries that you then send to Solr. So there's a lot of cool things you can do with query pipelines, and I think that people think about these less now. They're more used to thinking of index pipelines. So what does our product, Lucidworks Fusion, bring to the table? Well, basically, you can engineer pretty much any of the scenarios that I just covered, and ones that we haven't thought up yet, using the Lucidworks Fusion pipelines. And Fusion is based on Zookeeper like Solr, so it scales nicely, and it doesn't really modify Solr as you can, as I've shown in this talk, but it just leverages what Solr you already have, because it's basically a service-oriented architecture, not a Solr modification like our previous product was. So Fusion leverages a lot of the power of the things I'm talking about, and combining what the knowledge of what other users have searched for example, with the types of things that you're looking for now can really boost the experience. And for example, I bought a lot of things on Amazon, so I want the suggestions, which are things that a recommendation comes back with, be personalized, but also focused on what I'm doing now. As I said, I may be looking for jazz records right now, not want to get suggestions on things I've looked for in the past. So again, Lucidworks Fusion helps facilitate this notion that we can basically focus on what the user is looking for and what things are related to them. And as the great Charles said, tell me, what did I say? So with that, thanks a lot for your attention. Hopefully we'll have time for a few questions now. And feel free, though, to email me. My email address is ted.sullivan@lucidworks.com, or any of my colleagues at Lucidworks if you have more questions on this topic. So I'll turn it back over to you, Aaliyah, and happy searching.
Thank you, Ted. So we do have time for a few questions. We will now begin the question and answer portion of the session. Again, if we do not have time to get to your question today, a member of the Lucidworks team will reach out to you directly. So the first question for you, Ted, is does the autophrase.text have to be generated for each data set by hand?
Oh, that's a great question. Not by hand, it's just a flat file. So you could imagine that you could generate it programmatically. So it ends up just being a file where each line is a phrase. And I haven't actually built systems that use a programmatic approach, but I'm sure if you're, for example, if you already have an ontology or something like that, you know, or a data set, you could potentially build some pre-processing software that would build an autophrases file for you. They don't have to be manual, but humans are pretty good at doing this.
Next question. Is autophrasing included in Solr 4.10?
No, it is not. It is currently a JIRA submission, so you would have to get the software. It's on the GitHub site. If you Google autophrasing, you should be able to find my blog posts, and there's buildware in there so that you can build the jar file yourself. It comes with a built-in ANT build that works with 4.10. I've used it recently on this production application I was telling you about in Solr 4.10.3. So no, it's not in Solr yet. Again, there are a couple other solutions. As I said, it hasn't been committed, but it has been submitted to Solr, but it's not yet in the product. If it does, it will likely be in Solr 5, which is the current version. The good thing is you can use it in Solr 4.
Next question. How would I integrate named entity recognition with Solr, and what NLP software tools have you used or do you recommend?
Oh, that's a great question. Well, named entity recognition is sort of the entity extraction I was talking about, where you're finding types of things like persons, companies, and so forth. And I've used quite a few products. Some that come to mind right off the top of my head are this OpenCalais product that's produced by Thomson Reuters. It used to be a package called ClearForce, and I worked with ClearForce back when that was the product. There's also some open source things like OpenNLP, Mahout, that's actually machine learning. But there's a Gate framework from University of Manchester in England. So there's a lot of open source stuff that you can use to do NER, as well as packages like, commercial packages like OpenCalais, which is a web service, by the way. It's not, you don't have to download the software. Another one is SmartLogic. They publish to do a lot of this stuff with rules-based named entity extraction. And NER can actually can use machine learning approaches as well as some of these ontological rule-based approaches. So there's a lot of stuff you can use to do NER. A lot of the old search engines, or some actually currently competing with now, actually used to have these sorts of entity extractors built in. So there are just all kinds of ways. But to get it into Solr, all you really need to do is generate the metadata, tag stuff, and to put them in fields. And then, as I said, you can use that in the query autofilter. And I find that, as I was talking about, I find that to be a really nice fit because the query autofilter needs to be fast. It needs to rely on this crunching stuff that you do with NER to build this metadata or structure into your search index.
Great.
Okay.
So we're going to do
question.
two more. Yeah, we're going to do two more questions. But for anyone who has to jump off, since it is about time now, we will be sending out the recording of this presentation as well as a link to the slides in the next few days. So if you have time to stick around for the next two questions, that's great. And if not, you will get the recording shortly. So the next question for you, Ted, is you mentioned that the longest contiguous phrase wins when matching noun phrases in the query. Are there any clear examples where another strategy makes sense?
Well, yeah, that's a great question. In fact, I was actually thinking about this recently. So one of the problems that hits, and there was a slide that got edited out, and as you can see, probably for good reason, where I was searching for white linen shirts. Now, if you had a department store data set, where you're selling cosmetics as well as shirts, like Macy's or Sears would do, or Kmart, Target, whatever, you would have a brand of perfume called white linen. So if I had the phrase white linen shirts, well, clearly the user is not looking for shirts. So what the autophrase, I added some logic so that it would say, okay, white linen trumps white, but let me see if there is an equivalent match for white and linen. So both, now that I have a phrase that spans two terms, I have to find an equivalent phrase that matches white and linen, and sure enough it sees, okay, white is color and linen is a material, so it'll actually create a much more complicated query where it says white linen brand or white color and material linen. And what happens is there's no such thing as white linen, so that it will also look for perfumes that are white and so forth. So what happens in that case is that the disambiguation is a joint effort of the query autofilter and the search index itself. So even though it might come up with nonsensical Booleans, it does the correct ORing so that so that it works at the end of the day. Another example I just recently ran across in my music ontology. So I was thinking of having a query like Beatles songs by George Harrison. And in the ontology, I have things like a song has former Beatles, has composer, in many cases John Lennon and Paul McCartney, and in some cases George Harrison. But George Harrison also had some solo works that he also recorded. So what I really want is just Beatles songs by George, not all songs by George. And the solution there is just to put an additional piece of metadata that says this is a Beatles song. So if I'm talking about Let It Be, or that's a Paul McCartney song, sorry, if I'm talking about Something, that's a George Harrison composed song, that's a Beatles song. If I'm talking about All Things Must Pass, that's a George Harrison song that was also performed by George Harrison. So there may be additional tricks that you have to do in your metadata to squelch a longest contiguous phrase match, or make something that actually is more specific, because the user there, it doesn't really want to get things, and a lot of these topics are explained much more clearly in my latest blog post, so I'll just stop there and hopefully have time for one more question rather than ramble on this one. But it's a really great question and something I've been thinking about a lot in trying to improve this thing beyond just a sort of simplistic knee-jerk type of approach as the first implementations were.
Great. So the last question that we're going to take today is, how do we make use of concept relationships in improving relevancy?
Oh, that's another great question. And I ran across this recently with dealing with synonyms. So you're talking about related concepts. So in the area I'm talking about, you're talking about, George Harrison is a related concept to Beatles, for example. So if searching for Beatles, I should focus on, the group, the Fab Four, that is, not necessarily the individuals, but anything about Paul McCartney or John Lennon or Ringo or George is also relevant to the Beatles. It may not be exactly relevant. And in ontology, we call these things related terms. And one way to deal with this in Solr is, if we use filter queries, we're basically killing any relevance calculations that we might do. So this is where boosting and field-related queries come in. So if I tag things and I know that George Harrison is a related concept to the Beatles, I can then put related concepts in a separate field and then rank on them. So if the user searches for George Harrison, they will also hit on the Beatles, but since that's a related concept to George, they wouldn't be as highly rated as directly things that only talk about the late great Beatle that we all love. So that's one example of where related concepts are important. You really want them to affect relevance, not so much precision, because it's kind of about that, but not exactly. And precision, again, is more about what is right or wrong. So, and relevance is more about what's related to. I think the prefix RE is not an accident between related and relevance.
Great. So so that will conclude today's session. Thank you everyone for joining us today, and just a reminder that anyone who registered for this webinar will receive a link to the recording as well as the slide deck in the next few days. And if we did not have time to answer your question here, please look out for a note from someone on the Lucidworks team. Thanks again, and we hope you enjoyed today's webinar.
Yeah, thanks everybody for your attention. It was fun. Appreciate it.